Okay, so I'm going to try to look at a little bit more chain rule. I'm going to make a series of probably 3 or 4 little videos on this because it is really a truly robust topic that causes people a lot of issue. So I'm going to revisit a concept from the last video where we have a table of all sorts of values. I'm numbering this number 6 because the last video ended at number 5. But we're going to try to analyze these derivatives of these various points. So notice that h is f of g. K is actually g of g, which is a little interesting. So h prime of x, from our last video and also from class, it says it's the derivative of the outer function multiplied by the derivative of that inner function, then evaluated at the given number. So h prime of 1 would be f prime of g of 1 multiplied by g prime of 1. Now, of course, we're set up and ready to go because if I know what g of 1 is, that number 4 could go right in this spot right here. It says g of 1. So I'm going to change this to f prime of 4. And similarly, if I want g prime of 1, g prime of 1 is the number 2 right here. You can see that g prime of 1 is 2. Now, of course, the last little thing that I need to do is I need to find out what f prime of 4 is, because I kind of have to go through the process of a composite, and f prime of 4 is -8. So it appears that my product there is -16, and I'm done. I won't do all of these problems. I thought I would do a couple of them. H prime of 2, we're going back to the same story. It's f prime of g of 2 times g prime of 2. So I'm going to just grab everything off of the 2 column. And so if I need g of 2, I have the number 5. And if I have g prime of 2, I have the number 10. So f prime of 5 and g of 10. And then the last thing I need to do is I need to find the derivative of f at 5. So the derivative of f at 5 is -10, and I'm good to go. Now, for the sake of not being too long, and I also may have some students that want some help, let's take a look at k. K says it is g of g. Well, the rule that I just went over is then the derivative of k is the derivative of the outer function g multiplied by the derivative of the inner function. And so if we were going to say, let's find k prime of 5, I'm going to do g prime of g of 5 times g prime of 5. So I'm going to grab everything off of the 5 line. And I know that g of 5 is 2 and g prime of 5 is 20. So g of 5 is 2 and g prime of 5 we just said was 20. And then just like before, I need to go up and look at what g prime of 2 is. So g prime of 2, g prime of 2 is 10 right there, and we're good to go. So 10 times 20, we're looking at 200 would be k prime at 5. Now, I mentioned in the other one that we're going to go a little bit faster on some of these problems. So we know that the composite, this is the inside function, and something to the 10th power is the outer function. So what I'm going to do is I'm just going to start going a little bit quicker. So if I have something to the 10th power, its derivative would be 10 of those things to the 9th power. This is how the previous video, I mean, this is what happened in those. So we noticed that pattern so we could go quickly, because I would be letting u be 3x squared plus 7x. But then on the other one, we said y was equal to u to the 10th. So when we did dy du, which is what this is, we still had to multiply dy du, which is 10u to the 9th, by du dx, which was 6x plus 7. So I went ahead and wanted to write that one more time before I abandoned that viewpoint. So the next ones I'm going to be much quicker about. So if I were to express y as all of this stuff to the 1/3, if I were to take the derivative of the outer function, that's going to be that 1/3 is going to pop in front. We're going to reduce that exponent by exactly 1 unit. Then we're going to multiply by the interior portion of that, which gives me 2x. And it's always a good idea, if you can, to simplify things just a little bit. So I'm going to take just a little bit of time to say that if I've raised it to the 2/3 power, it is a cube root that has been squared, and because it was negative, it went to the bottom. Number 9, the derivative of a secant is a secant tangent. But of course, how chain rule works is I took the derivative of the outside function times the derivative of the inside function, but the derivative of that is just 0.03. Okay, number 10, very similar to the one above. Y prime would be 2/3 times the stuff on the inside. We're going to drop that by 1 unit down to negative 1/3. We're then going to multiply that by the derivative of the portion that's in the inside. So I've got 10/3, and now I've got a cube root of 5x plus 1. So hopefully so far, so good. Now, number 11, I did choose to make one that's a little bit harder. This is actually introducing a chain rule that actually has a little piece of a quotient in it because we do have a division. So when we go through this problem and I go with my low, d high, that's all good, minus high, here's the problem. When I do the d low, when I take the derivative of e to the 3x, I get e to the 3x. That's e to the u, but the u part being 3x, the du part is 3. All over e to the 3x quantity squared. Now, what is actually very convenient about this particular problem is that you will notice that the numerator has both terms having an e to the 3x in it. So if I factored that out, I'd be left with a 1 here and a minus 3x there, and the bottom has this e to the 3x squared. But this tends to happen on these exponential problems. You notice these have something in common. The top and the bottom have an e to the 3x. So I'm going to divide the top by e to the 3x, and that just leaves this other argument. And when I divide the bottom by e to the 3x, I get e to the 3x. I will say this is a part of chain rule that sometimes bugs people, is because you kind of don't know how far to go in your simplification. Some cases it's fairly simple because you have a negative exponent. Other cases, especially in quotients, you have a little bit more work to do. And then my last problem, this is just going to whet your appetite towards the last one, is this is basically a multi-level chain. Because if you say y is the sine to the 5th, that's saying I've got the sine of the cosine, which is a little bit ugly, and all of this is to the 5th power. So my chain rule would say, let's take the derivative of the outside function. So it's 5 of all of those things to the 4th. Now I kind of dealt with that portion. Now I go inside, and I know the derivative of the sine is the cosine. But again, just like before, I'm going to leave the interior portion alone. So it's the cosine of the cosine of 3x. Then I've got to go into here and take the derivative of the cosine, which gives me a negative sine of 3x. And holy smokes, it never ends. Then I have to go all the way to the inside and take the derivative of 3x, which gives me 3. Look at all of that stuff. That would be my answer. So I would probably do one very small thing. I'd probably pull the 3, the 5, and the negative out in front. I'm going to express the sine of the cosine of 3x quantity to the 4th power. I've got the cosine of the cosine of 3x and the sine of 3x. And boy, that's a tough one. This is a problem right out of the Butte College set. So this is just kind of where they go pretty quickly. And so hopefully that's helpful, and I'll probably be back for a video number 3 down the line. Okay.